All right, so let's get started. So I want to talk about something very special to my interest, in the sense that I would personally like to learn and understand this concept at a deeper level. And usually in textbooks, I mean, most often in the, at least in a lot of the modern textbook, this is not quite touched upon in a very geometric way. So what I plan to talk about today is the concept of torsion. Okay, I, especially in the context of Riemannian geometry, which is the course that we are pursuing. Okay, so the material here is more or less sort of taken from various sources. So there is no one textbook that I can actually recommend, but there will be a few references along the way. But the point being, we have talked about metric compatibility last time, and along with torsion free, these two are the two key conditions which guaranteed the uniqueness of the Levi-Civita connection. Okay? And remember, we talked about what torsion is and what metric compatibility is. So let's get started. Okay? So in general, torsion is a mysterious entity, and I've already said about the other part that it's usually the treatment is algebraic rather than geometric. Okay, it's a mysterious entity even more so simply because the notion of torsion doesn't quite make sense for a connection on a general vector bundle. And this is something we had talked about in class, because you cannot talk about the Lie bracket of a vector field with the section of a general bundle. So this is very specific to the tangent bundle. So that probably makes it even more special. But for those of you who might not remember the formula correctly, this is what torsion was defined to be, right? So given a connection nabla on the tangent bundle, you define the torsion to be this quantity, which is the covariant derivative of y with respect to x. And then you switch x and y and you take the difference. It turns out that the difference is not quite a tensor, but then when you subtract off the Lie bracket, then that turns out to be something which is nice. Okay? It turns out this is a tensor, and asking for the tensor to be 0 is a rather natural and also a beautiful algebraic condition. Okay? Remember, in metric compatibility last time, we encountered the equivalent definition that nabla of G was 0. But G was the Riemannian metric, and nabla of G means you covariantly differentiate the Riemannian metric. And that is a tensor, because the Riemannian metric is a tensor. So we are asking nabla of G to be 0 is equivalent to metric compatibility. Here we are asking T nabla, the torsion, to be 0. And when that happens, you call it torsion free. Okay? So it's a nice condition, at least algebraically. Our purpose for this talk is to explore what are other ways of interpreting this quantity called T nabla or torsion. All right. Okay, so we have seen already that if you write the connection in local coordinates, then you can take your capital X to be the vector field d by dxi, capital Y to be the vector field d by dxj, and in those local coordinates, the d by dxi is commute with the d by dxj, so the Lie bracket does not contribute. So in that case, what you're left with is the Christoffel symbols coming from the first term minus the Christoffel symbols coming from the second term, and those two should be 0. But that basically boils down to saying that gamma kij is gamma kji, okay, which effectively says that the Christoffel symbols are symmetric in the lower indices. Okay, so this is something we have seen. You simply write down the connection in local coordinates, and this is an equivalent definition of a connection being torsion free. It's simply requiring that the Christoffel symbols are symmetric. Okay. Okay. So that's one interpretation, the first interpretation, which is just symmetry of some bunch of symbols which transform according to certain rules. So you can patch them up from local answers to a global things to obtain nabla. Okay. Now, what about a different interpretation? And so, I mean, as we see different interpretations, you might choose your favorite, but let's see another one. So last time we had seen how to extend the covariant derivative nabla to T star n. right? So basically we said that if you have a connection on Tm, you can extend it to a connection on T star and higher order tensors as well. Okay, so this is how it was defined. So a connection on T star M is simply going to be, you should be able to covariantly differentiate a section of T star M, which is nothing but a smooth one form, along a vector field X. That's what a section of Tm is. So you should be able to differentiate one forms along vector fields, and that should be producing another one form. And how do you evaluate this one form? So this nabla alpha in the direction of X, this one form is determined by evaluating this at a vector, because the one form is basically a collection of covectors indexed by the manifold. So this is determined by evaluating this at a vector, but that simply means you take X acting on alpha of a vector field. Alpha of a vector field is a function, X of a function makes sense, minus the one form acting on the covariant derivative of the input vector field along X. So that's another vector field, and then alpha is being a one form acts on the vector field, gives you a function. So this implicit definition determines nabla X alpha. This is what we talked about last time. Okay. So you have a connection on T star M. So we are going to exploit this and talk about what torsion free means for this connection. And you should be careful in the notes as well as in what I'm going to say. I'm using nabla for the connection here. I'm going to use nabla for the original connection also. I'm going to make an abuse of notation and not call this nabla tilde or anything else. I'm still going to call this nabla. Okay? But this is a nabla on T star M. The original one is a nabla on Tm. All right. So any questions so far? Okay. So just keep this in mind. So this is what you have. You can covariantly differentiate one forms along vector fields. Okay. So what you could do is you could pair T star M with Tm, right? Why? Because a one form can eat up a vector field and produce a function, which is saying that a covector can be paired with a vector, and that gives you a scalar pointwise. So you can define a new map, which I'm going to call nabla bar now. It's going to be a map from sections of T star M to sections of T star M, tensor sections of T star M, sorry. So this is it's a different kind of a map. See, the earlier map was going from sections of Tm, cross sections of T star M to sections of T star M. I'm claiming now we can define a map which sort of goes between the same kinds of vector space. If you call this thing V, then this is like V goes to V tensor V. Okay. So how do I define this? Well, you choose an element alpha 1 tensor beta 1 up to alpha L tensor beta L in the right hand side. So the right hand side is a tensor product of V with V, which means any element in V tensor V is a finite linear combination or a finite sum of elements of this type. That's what a tensor product is, right? So let this be an element such that it has to satisfy some criteria, such that I want this to happen. Okay? So remember, alpha is my fixed, alpha is a one form which goes as an input from the domain. So I choose an alpha in omega of T star M, that's a one form, and I want to define nabla bar of alpha. I'll be defining nabla bar of alpha to be this sum, alpha 1 tensor beta 1 alpha L tensor beta L, such that the alpha I tensor beta I, this sum, satisfies this equality. That if I covariantly differentiate alpha along X, that one form should be nothing but take alpha 1 and multiply it with the one form beta 1 acting on X. So beta 1 of X is now a function. Function times alpha 1 is again a one form, and then you sum over all such terms. Right? So both the left hand side and the right hand side are one forms. So what I'm asking is, I'm looking for an element alpha 1 tensor beta 1 up to alpha m tensor beta L, an element of T star, one form tensor one form, such that this equality holds for all X, for all vector fields X. Okay. So that's going to be my definition of nabla bar. So nabla bar of alpha is going to be this finite sum. Okay. And this clearly lives in sections of T star and tensor sections of T star. Okay. So I haven't talked about why there's an element to begin with or why there's a unique element. But if there is an element, I'll define nabla bar of alpha to be this element of sections of T star m, tensor sections of T star m, all right? So the exercise, which again you can probably verify by writing things down in local coordinates, and it's just using the fact that B star can be paired with B. Okay, and I'll leave it to you to check that. So show that there's a unique element in sections of T star m, tensor sections of T star m, like so here, that satisfies this thing for all x. So there's a unique such element, and you define that to be the image of alpha under nabla bar. Okay. So are there any questions so far? Okay, so we'll be actually doing a local computation very soon. So you'll see all of these will be fleshed out in terms of xi's and d by dxi's and dxi's. But this is just a formal exercise in linear algebra, so to speak. Okay. Okay, so you define nabla bar alpha to be this unique element alpha 1 tensor beta 1 dot, dot, up to alpha L tensor beta L. Okay. So ideally one should write down nabla bar in local coordinates and see what is exactly going on. Okay. So the exercise is still up there, but we'll write it down locally because we have to compute certain things. So remember what should nabla bar do? Well, if you choose a local coordinate coming from a local chart, the local coordinates are x1 through xn. So the one forms are going to be of the form summation fi dxi, I goes from 1 through n. So these are functional linear combinations of the dxi's. So if I take nabla bar of dxi, I should be able to express that as a combination of dxj tensor dxk's with some coefficients. Okay. So before we do that, you should keep in mind one specific thing. That specific thing is the right hand side looks like V tensor V, and whenever you have V tensor V, this tensor product decomposes, I mean in general even the V tensor N decomposes into the symmetric and the antisymmetric, but I mean V tensor V decomposes into the symmetric and the skew symmetric or the antisymmetric part, meaning if I choose a vector of the form little v1 tensor little v2 plus little v2 tensor little v1, that's symmetric, whereas little v1 tensor little v2 minus little v2 tensor little v1, that's skew symmetric. And any vector can be decomposed into a sum of these two in a unique way. Okay. So what you have to show is that if I take the skew symmetric part of this gamma t star m tensor 2, then what I get is a skew symmetric 2 form, because it simply looks like a wedge of one form with a wedge of one form, and that's precisely the space of differential 2 forms. Okay. So, and you'll see why we really care about the 2 forms in a minute, because if you go back and look at the domain of nabla bar, the domain of nabla bar is 1 forms. The codomain or the range is not 2 forms, but it's something which contains 2 forms. And so you can always sort of project from V tensor V to the skew symmetric part, for example. So if you do that, it'll be, if you compose the projection from sections of T star M, tensor sections of T star M to its skew symmetric part, you will simply end up getting a map from sections of T star M to omega 2 of M, which means you're simply getting a map from the 1 forms on M to the 2 forms on M, simply by post-composing nabla bar with the projection to the skew symmetric part. Okay, so that's why this is relevant. It's going to be relevant in the next slide. Okay. But are there any questions before I move on to the next page? All right. So we're going to write things down in local coordinates. So let's see what's happening. Okay. So yeah, this is what I just said. So you can actually project this nabla bar to the skew symmetric part. So what do you get? See, the sections of T star M is 1 form, as we just discussed. And when you project V tensor V to skew symmetric part of V, in this particular context, you get 2 forms. So you're getting a map from 1 forms to 2 forms. So at this point, you might ask yourself the question, do we know of any such map which takes 1 forms to 2 forms? And what is a map that comes to your mind? You can probably, if you have something in mind, you can say it. Anything that you have seen in differential geometry in say the last semester? Okay, so I guess so probably people know this. So see, you already know that the Dirham differential maps precisely in this fashion, that it maps k forms to k plus 1 forms, right? So you already have this map, right? The Dirham differential. So the question really is whether these two are the same. And it turns out that this is equal to the Dirham differential if and only if the original connection nabla is torsion free. Okay. See, torsion free for, I mean, the connection nabla on T star M being torsion free again doesn't make sense, simply because you cannot compare things and you cannot talk about Lie bracket of two one forms. But this nabla is the original nabla. So this is a nice condition which says if you somehow think of the connection now as a connection on T star M and then just flip it over and get a map of this form, the skew symmetrization, then the skew symmetrization is simply the natural map D if and only if the connection is torsion. If you are more of a differential geometer, this is something you might like if you like to compute things with cotangent bundles and their powers. Okay, so this is an exercise with a star because this is not too hard, but it's an exercise with a star because you have to do a little bit of work, write things down in local coordinates and so on. And this is, I think, part of it is already assigned to somebody's project. So I mean, we'll wait for the projects to be done maybe or handed in, and then I can discuss this at a later point. Okay. But this is the third criteria, that either the Christoffel symbols are symmetric in the lower indices, or you can take this to be an alternate definition or a criteria. That you transpose, you take everything to T star M, and now take the skew symmetric part, and that has to be equal to T, right? So, okay. Okay. So now I want to sort of make a further remark before we get to the real sort of heart of the matter. So see, we are extended this covariant differentiation via the connection to all tensors of the form PQ or all PQ tensors, right? A PQ tensor for us is simply going to be nothing but the section of this abstract bundle, which is take TM tensor, TM tensor, TM, P copies, and then tensor that with Q copies of T star M. So whatever this big bundle is, sections of that, so that's another vector bundle, sections of that is called a PQ tensor. All right. So what we could do is we could say that, okay, if I have a function f, I can look at df, right? So here, of course, when I say df, this df is the same as the capital D. I've been using capital D, but I'm using little d here to be compatible with the Dirham differential. So what is df? Df is now going to be a one form, right? Because f is a smooth function. So a one form is a 0-1 tensor because it's sections of T star M. So I can apply the connection nabla. And remember, what does nabla do? So nabla is now going to basically map, just a second. Yeah, so it's going to basically produce a 2 tensor, I mean 0-2 tensor, okay? Just a second. So, so what you want is, so I think I spoke too soon. So you can always talk about this tensor simply because we have extended this to all tensors and we know what happens. So the point is, if I look at this quantity, I expect certain symmetries of this quantity, and I'll say what in a minute. And for those of you who have read the slides, you know it already. So we define this tensor to be the Hessian of F, okay? And why is it defined to be the Hessian? Well, at least symbolically, what is a Hessian? A Hessian basically is, typically it's on Rn setup, you simply have a function f and you look at del 2 f by del xi del xj. Consider this matrix, and this is a matrix which acts on two tangent vectors, one as a column, one as a row on the left, right? So that it acts on this, so it's sort of like an inner product, and the usual Hessian on Rn is symmetric. Okay. However, the issue with the Hessian is that the usual Hessian is not a well-defined object unless you are at a critical point. And even when you are at a critical point, you have to choose sort of coordinates and then calculate the Hessian. So the determinant of the Hessian is perhaps a well-defined quantity, but if you are not at a critical point of f, the Hessian is not a well-defined quantity, okay? Or any relevant information that you want to extract out of the Hessian, the signature, the determinant, none of these things will make sense unless you are at a critical point of f. So you cannot talk about the Hessian of f in general as a global object, okay? However, in this case, if I define this to be the Hessian, this does make sense as a global object. This is a 0-2 tensor, which is basically saying that it's an element of sections of T star M tensor T star M. So it would do the same job as the usual Hessian, that it will input two, given two tangent vectors, it will input that and it will output a number at every point. Okay. So the reason why it's called a Hessian, I'll leave it to you to check that in the usual examples where M is Rn or something like that, this does agree with the usual Hessian wherever it does make sense, if your connection is chosen appropriately. But this has the advantage that this is a globally defined 0-2 tensor. Okay. So I mean, differential geometers or people who do geometric analysis do care about this quantity. And I'll not say much more about this, but this is an important quantity which people care about. And just taking a clue from the usual classical case that where the Hessian, wherever it is defined, is symmetric, you might want this thing to be a symmetric 0-2 tensor. Okay. And it turns out this is usually not symmetric, but it's symmetric if and only if the connection nabla is torsion free. So torsion free also recasts itself as symmetry of this new Hessian. This is often called the Riemannian Hessian because it requires a connection. Okay. So this is the third or the fourth interpretation, if you want. Okay. But I'll leave this to your imagination for the most part. You can work out simple examples, but I just wanted to say that this is another thing which people do care about and it's useful. Okay. Okay. So the rest of the talk is going to be focused on a particular example and then the actual geometric meaning, as far as I understand, of what a torsion is. So before we move on, are there any questions? Okay. All right. So yeah, so we have seen four seemingly different criteria, but all of them are equivalent. But none of them really says something which you might call geometric. Okay. So let's begin with this example. This is due to Elie Cartan, and he basically introduced this notion of torsion way back in 1922 when he was investigating certain things in physics and gauge theory and so on, or at least it might not have been called gauge theory, but it's something to do with general relativity and things like that. So he introduced this concept and this example in particular. So this is attributed to him. It's called Cartan's spiral staircase. All right. So this is a very simple example on the face of it. You take R3. This is your usual Euclidean R3, and the Riemannian metric on R3 is the standard Euclidean metric. Okay. However, in this example, we're going to construct a connection which is not the Levi-Civita connection. This is a new connection. So what are the vector fields? Well, you choose, I'm going to denote the vector fields d by dx. So I have three coordinates, x1, x2, x3. So del by del x1, these are the horizontal vector fields. I'll denote them by capital X. Del by del x2, these are the vector fields along the y-axis. I'll denote them by capital Y, and del by del x3, these are the vertical flow lines or the vertical fields, and that I'll denote by capital Z. Okay. So is the notation clear? So I'm often going to switch between capital X and del 1, but del subscript 1 simply stands for del by del x1, right? Okay. So, all right. So I want to define a connection here, and I've written, so there's a small typo, but I mean, it's not that much of a big deal because you know what I meant here. So this is sections of tangent bundle of R3, right? Because M is my R3, so sections of TM, cross sections of TM, sections of TM. So these should all be T of R3, T of R3, T of R3. If you have the notes with you, just make that change or make a note somewhere. So how is it defined? Well, we're going to use something very unique to R3, the cross product. So if I want to define the connection, it suffices to define the connection on these three spanning vector fields, because any general vector field is of the form f times capital X plus g times capital Y plus h times capital Z, because any vector field is a functional linear combinations of the d by dx axis, right? And then by Leibniz rule and the C infinity linearity, I know what nabla xy is for any two vector fields. So it suffices to define nabla on these basis vector fields, and I define nabla of dj along the direction del by del xi to be the cross product of del by del xi with del by del xj. So that's a new vector field. Okay, so that's the definition. So remember, whenever somebody says define it to be this, it's understood that you define it on the appropriate basis, and then you extend by C infinity linearity on the subscript slot and Leibniz rule on the actual slot upstairs. Okay, so that determines nabla over all of sections R3 cross sections R3. Yeah, so that's what I just said. Okay. So just leave it here. So we'll explicitly write down what happens for nabla xy, for example, and the other combinations. So we'll see what's going on. Okay. So it's clear that the covariant derivative of del I along del I is 0, because del I cross del I is 0. The cross product of v cross v with itself is 0. So del i's are being covariantly differentiated along del i's, and it will give you 0. But what about the other things? So okay, so before I say that, there's an exercise, and the exercise basically says whether you have understood the C infinity M linearity and the Leibniz rule. So if I take any general vector fields, two of them, x1 which is f1x g1y h1z, and x2 which is f2x g2y h2z, I should be able to calculate this, right? Nabla x1 x2. But I'm saying that this thing simply becomes, it looks like a long quantity, but that's because you have to use the fact that it's C infinity R3 linear in x1. It satisfies the Leibniz rule in x2. So if you followed that step and if you expand, this is what you'll get. Okay. So this, I mean, there will be these many terms, but it's not too hard. There's some antisymmetry going on. If you look closely, you'll see that these terms are of a certain type, and then yeah, so I think there's just a second. Yeah, so there is a typo here. I think, see, the first line is correct. In the second line, the first set of x's, so x of f2, x of g2, x of h2, these should be capital Y. So capital Y of f2, capital Y of g2, capital Y of h2. And in the third line, instead of the first set of x's, it should be a z. Z of f2, z of g2, z of h2. Okay? Everything else is correct. So anyway, so you get these 15 terms, but it's not anything very complicated or deep, because you simply have to sit down and write down what Leibniz rule and C infinity R linear, R3 linear is. Okay. So anyway, so I'm sure all of you can do this, and this is an exercise, so it's colored in red. Okay, but the first thing that you might want to verify for any connection is, first of all, whether it's metric compatible and if it's torsion free. If it's both, then we know that it has to be the Levi-Civita connection, and we know what that is, right? So let's see what happens. So you know that if I take the vector fields y with z, the dot product is 0, because y is del by del x2, z is del by del x3. The dot product is 0. So if you differentiate 0 with respect to x, that's still 0. On the other hand, if you calculate this quantity, what is this? Well, what is nabla xy? Well, nabla xy is simply x cross y, but x cross y is going to be z, right? Because the cross product of the x-axis or anything along the x direction with the y direction is something in the z direction, and these are of unit length. So nabla xy is z, inner product z with z is 1, because it's the usual Riemannian metric on R3. What about the other term in metric compatibility? Well, it's this term, right? But what about nabla x of z? Well, this is x cross z, but x cross z is minus y because z cross x is y. Okay, so you get inner product y with minus y, but that contributes a minus 1. So the sum is 0, but it's also 0 on the left hand side. So that precisely tells me that this connection is metric compatible. Okay? So I'll just pause here. I'll just let you look at the details and see if you have any questions. Okay, so it's metric compatible, which is good. So at least it's metric compatible in this particular example of XYZ, but I'll leave it to you to show that this is metric compatible in general. So you just choose any three triple of vector fields and the same identity is going to be true. It will not be 0 on the left, but this identity is going to be true. So it is metric compatible. Okay. So what is evident is that it's not torsion free. Why? Because you simply calculate the torsion of d by dx1 with d by dx2. That will be nabla xy minus nabla yx minus the Lie bracket. Well, the Lie bracket of d by dx1 with d by dx2 is 0 because the flows commute. And what is this quantity? Well, this is z. What is this quantity? This is minus z because this is y cross x. So z minus minus z, that gives me 2z. So this is definitely non-zero. So there's some torsion. And you can work out what will happen with torsion of y with z. Okay, it is going to be 2z, and torsion of z with x is going to be 2y. It's kind of cyclic that way because you're using cross products. All right, so this is not torsion free, but it's metric compatible. All right, so let's analyze this further. What kind of geodesics do we get? And by geodesics here, I mean geodesics of the connection, not geodesics of the usual metric that we know are straight lines. Okay. And what does this non-zero torsion have to do with the spiral staircase? All right. So are there any questions so far? All right. Okay. So try this exercise. This is a small, like a couple of lines. You just have to sit down and carefully check those things. And I pointed out the 2 lines where there are typos, and the signs I think are correct to the best of my knowledge. So, all right. So let gamma be a geodesic, and here I mean a geodesic for the connection, okay, not for the Euclidean metric. So that means that I look at gamma prime. What is gamma prime? Well, gamma prime is A prime d by dx1, b prime d by dx2, c prime d by dx3, which I write as A prime capital X plus b prime capital Y plus c prime capital Z, because these are my global vector fields. And being a geodesic with respect to the connection means it should satisfy this equation, right? Okay, so now we expand. So we know that it is C infinity linear in the subscript, right? Which means I could simply take all of these out and separate them, and I'm simply calculating nabla of A prime X acting on these 3 things. And I can even pull out the A prime, so it's going to be nabla of X acting on all of these 3 things, right? So when nabla of X acts on this, well, what happens? Well, the first term is X acting on A prime, that is the Leibniz rule. The other X remains the same, or the A prime comes out and then you get nabla of XX, right? So I'm saying concentrate on nabla of A prime X acting on this A prime X. So you can pull out this lower A prime already because of C infinity linearity, and then you're left with nabla of X acting on A prime X. That has 2 terms. X of A prime into X plus A prime into nabla of X along X. But nabla of X along X is 0 because X cross X is 0. So you only get 1 term from the first term in the subscript and the first term here. Is that clear? Okay. Now what about the next one? Well, the next one is similar, right? So you look at how A prime X, so how nabla of A prime X differentiates B prime Y. So again, you can pull out the A prime and then either X acts on B prime, which gives me this term, or the B prime also pulls out and I get nabla of X, Y. But nabla of X, Y is Z. So that's why the 2 terms, this is due to Leibniz rule, okay? So if you can follow the first line, the others are going to be similar. So we're going to now do the same thing with the third term. So let's see what you get. So A prime can be pulled out. You're looking at nabla of C prime Z along the direction X, which means either X acts on C prime, the Z stays the same, or C prime comes out and then it's nabla of Z along X. But that is minus Y. So that is this, right? So you get these 5 terms. And I've color coded them so that, especially if you're looking at it on the screen, not necessarily in a printout, then you know which terms are Z, which terms are Y, which terms are X. And sometimes cancellations are easier to see. So that's why the color coding, okay? So this is just Leibniz rule and C infinity linearity for the first term in the subscript. You can similarly work out the second term in the subscript, B prime Y, and all these 3 terms. So I'll let you go back and read through the notes, but you can be ascertained that this is what you get, okay? You'll get 5 terms always, because whenever you have nabla B prime Y covariantly being differentiated along B prime Y, this will only contribute 1 term, because nabla YY is 0. Okay? Same with Z. You get 5 terms, and that's it, okay? So you want this to be 0. So now if you look closely, you see that certain things cancel. So for example, B prime C prime X from the second line, the last term, cancels with B prime C prime X from the third line, second last term, right? These two. Similarly, A prime C prime Y, the last term from line 1, cancels with the second term from line 3, A prime C prime Y, okay? And so on and so forth. So a lot of these things will actually cancel. Say, like you look at A prime B prime Z in the second term on the second line, that cancels with the third term on the first line, A prime B prime Z. So all of these cancel, and what you're left with is this. So I wrote this without maybe adding one more line in the middle. But why is this true? Well, this is true because remember what is happening. You look at all those things. So you look at things with A prime, okay? So, I mean, just look at the first term in each of the lines above. You have A prime, X of A prime X, B prime, Y of A prime X, C prime. Sorry, there should be a, just a second. Just a second. There's one term that I'm missing here. I mean, I'm not missing anything per se, but no, there's something. I think I have to simplify things a little bit. So maybe I'll rectify that and then send the slides over again. There's something that I'm missing, but the conclusion is still true. The conclusion that I'm going to say. So yeah, so I apologize for that a bit. So the conclusion should be that the geodesics for even this connection is still the same straight lines that you get in R3. Okay? The straight lines in R3 are geodesics, and even for this connection, the geodesics should turn out to be straight lines. Okay, so if you can get to this, then of course this last equality implies that it's a straight line, because that says that A double prime is 0, B double prime is 0, C double prime is 0, which means A is a linear function, B is a linear function, and C is a linear function. Okay, but one has to apply chain rule and then just see how the terms simplify, which I think I don't see it immediately. Even though the terms cancel, there are certain other things that you have to check. But yeah, but so let me leave it at that. Okay, but it is going to be a straight line. So that is an observation But what we want to do is now we basically want to parallel transport a vector along a geodesic of the connection or a straight line. So we'll choose a straight line, one of the axes, and then we'll parallel transport this vector along this axis using the connection and see what we get. Okay. So this is a very concrete example of a parallel transport, perhaps the most concrete that will compute and work out, apart from the spheres and so on. So I mean, that's what we're going to do. All right. So are there any questions here? I mean, I'll just pause because I think that there should have been an equality in the middle explaining certain things, but I'll rectify that maybe in the next email. All right. So any comments or remarks so far? Okay. So, all right. So I want to parallel transport the vector 1, 0, 0. And this is a vector pointing in the x-axis direction. This is of unit length. And this is a vector I'm assuming at the origin. Okay? The vector 1, 0, 0 is a tangent vector at the origin. And I want to parallel transport this along the z-axis. And the z-axis is a geodesic by the previous computation, or you can even check otherwise that the z-axis is a geodesic of the connection, simply because you will have nabla zz, but nabla zz is 0. That's what gamma prime is, right? So gamma prime is 0, 0, 1 as a vector field. So it's simply the vector field z. And that clearly is a geodesic of the connection. So you don't need the first part. But nonetheless, so we want to parallel transport this vector 1, 0, 0 along the z-axis. So what are we solving? We are solving for a vector field x of t. I'll write them down in 3 coordinates, a, t, b, t, c, t, such that at time 0, this is the vector 1, 0, 0. And otherwise, xt is a tangent vector at gamma t. And it satisfies the parallel transport equation that the covariant derivative of x along gamma prime should be 0. Okay. So this is an equation we can write down and solve. So this capital X is not the same as the old capital X. Okay. I couldn't bring myself to use x tilde or anything simply because it would look bad. But this capital X is just a solution of this equation. The old capital X is the standard vector field d by dx1. Just make that distinction in your mind. All right. So what is this quantity? Well, this is simply nabla of del by del x3. I'll call it del 3 of a del 1 plus b del 2 plus c del 3, because remember my x in coordinates was at, bt, ct. So as a vector field, this is a del 1 plus b del 2 plus c del 3. So what is this quantity going to be? Well, it's going to be del 3 of, so if you look at nabla del 3 of a del 1, you have to use the Leibniz rule. So it's either del 3 of a times del 1 or a times nabla del 1 along the direction del 3, but that simply means you're crossing del by del 3 with del by del 1. So that is y, which is del by del 2, right? So this is just saying nabla y covariantly differentiated along z is x. That's all. Okay. Sorry, nabla x covariantly differentiated along z is y. So these two terms appear out of the first term by the Leibniz rule. Is this clear? I mean, it's a simple thing, but the notation might be a bit off-putting. So I'm using this notation because it is easier to symbolically do things. Okay. So what about the next term? Well, the next term is also going to have the Leibniz rule property. So either is going to be del 3 of b or times del 2 or b into del 3 del 2, which is minus del 1. Right? And remember, what is del 3 of a? This is simply going to be nothing but like del by del x, del by del x3 of a, the function. Anyway, so we'll see what this is. It basically simplifies a lot. So this is what you get, right? If I apply Leibniz rule on the second thing. So it's minus del 1 because nabla del 2 with respect to del 3 is minus 1, the cross product. And similarly, you get exactly one term here. Why? Because remember, nabla of del 3 is 0. Okay. All right. So what is this quantity? This is simply del 3 of a minus b, a plus del 3 of b, and del 3 of c. So the only terms that Yeah, so the only terms that remain is basically del 3. And these things involving del 3, and that's understandable because our curve is 0, 0, t. So when I say del 3, it's simply d by dt because that is the z direction, right? So we basically want to solve this thing to be equal to 0, which means you have three equations. You have that d by dt of c is 0, a plus d by dt of b is 0, d by dt of a minus b is 0. I have three equations. So the last equation tells me that c must be a constant, but c of 0 is already 0. So c must be the identically 0 function. And a and b should satisfy some form of sine and cosine because it looks very much like a prime is equal to b, a is equal to minus b prime. So we can show that at equal to cosine t, bt is equal to minus sine t. It sort of goes in the clockwise fashion, and ct is identically 0 is the solution for this equation. Okay, that's something you can simply even check because I've told you. So that's it. So you know what x is, right? So any questions so far? Okay. So the point is, if you parallel transport this vector 0, 0, 1 as you move up in the z direction, it starts turning. That's what this is saying, right? It's not, see, in the usual Levi-Civita connection, if you parallel transport 0, 0, 1 vertically upwards, it will stay the vector 0, 0, 1. But now you're actually turning. So that's what's happening, okay? So I'll show you the picture in a minute. But before that, just note that the length of xt is constant, okay? And that's understandable because the connection is metric compatible. So lengths of parallel transported vectors are preserved along geodesics. That's something we have seen, okay? And similarly, this x of t is always perpendicular to 0, 0, t. It's always perpendicular to the z-axis because the only things that happens are in the xy coordinates, ct is 0. And that is also understandable because if you have a metric compatible connection and you parallel transport a vector along a geodesic, then the angle between the parallel transported vector and the geodesic stays the same because it preserves the metric, right? That's what metric compatible means. So it's understandable that that will happen, but it sort of starts turning. Okay? So it rotates along the geodesic. So yeah, and so if you trace out the tip, this is a helix. So I'll come back to this remark in a moment. So this is the picture, right? So you start off with this as your initial vector, 0, 0, 1. Oh, sorry, 1, 0, 0. And then you, as you move up along the z-axis, which is your geodesic, the parallel transport basically tells you that you should be moving this red. So this is, the red arrows are the images of the parallel transport of the curve of the vector 1, 0, 0 as it moves up. So if you have moved up here, you would have, this looks like this, and then it will, so the tip of the parallel transported vector actually traces out this helix or a spiral centered along the axis z. Okay, so it's sort of, so although the length here looks larger, but this is just a perspective. These are all of length 1, the red arrows. Okay? So this is what actually happens. So the parallel transport in this particular case, when you start moving this thing, actually traces out something which looks like a spiral staircase, and hence the name. Okay. So I'll pause here for a minute. Are there any questions on this picture or whatever we have discussed up to here? Okay. So the point is that if you have the Levi-Civita connection, the parallel transport would simply have translated the vector 1, 0, 0 just upwards vertically, so that the tip of the parallel transport in that example would trace out a line parallel to the z-axis. In this case, however, it's a staircase because it's rotating, but see that the angle between the z-axis and the red vectors are always 90 degrees, and the length of the red vector is always 1. So that's an illustration of metric compatibility. Okay. Okay, so let me go back to the last remark. See, the last remark that I said here is that the tip of the parallel vector field traces a helix, and you know very well that a helix is not a geodesic, either for the connection or for the Riemannian Euclidean metric. So the helix is not a geodesic, And this is precisely the phenomena which, or the more general version of the phenomena which is usually happening in metric compatible connections which are not torsion free. So whenever you have a metric compatible connection which has torsion, if you take a geodesic and you take a small vector and you parallel transport this vector, the tip of the vector will trace out a curve. Okay? But then this curve itself may not be a geodesic, and the failure of that tip of the parallel transported like vector being a geodesic is somehow being captured by the non-zeroness of the torsion. That's the remark that I want to say here. Okay, I'll say more about that in a minute, but I think for now this is that illustration. All right. So let me move on to the next slide then. Okay. Okay. So to see what's really going on, I mean, one would really like to now, instead of the connection, talk about parallel transport, because parallel transport, remember, is something which is a lot of data, but having parallel transport and differentiating that gives us connections. That is how we motivated, I think, connections in the beginning in the usual lecture, that we said that if you have a notion of parallel transport, then you can use that to compare the velocities at two different points. Okay. And just a second. Okay. Sorry about that. Okay. So if you have a notion of parallel transport, then you can differentiate that and get a connection. How do you do that? You simply choose a curve and then you can take gamma prime at t and gamma prime at t plus delta t. These are two velocities at different points, but you can use the parallel transport to bring gamma prime at t plus delta to the tangent space at gamma t, and then now you can subtract and take a limit. And that defines the covariant derivative that we know. So parallel transport is sort of, in some sense, which gives you connections, and you can recover a parallel transport from the connections by parallel curves. So it makes sense to look at the parallel transport. So again, we want to parallel transport delta 2, the vector field delta 2 along the x-axis, but I'm choosing epsilon because in the general setting I want my vectors to be sufficiently small so that whenever I do all these things, they happen in a local chart and I can make sense of everything in a local chart, right? So remember I said look at the tip of the parallel transported vector and it traces out a curve, and nobody objected at that point, but perhaps you should have, because in general if I have a vector and I parallel transport that vector, what I get is going to be simply a vector field along a certain curve, right? But I cannot really now talk of the tip of that vector field and think of that as a curve in my manifold, because you simply cannot. However, we can do that if you assume that these vectors are sort of under the images of the exponential map. So you can take the inverse image and then it traces out a curve in M. But that only happens if you're working in a small chart. Okay, so that's the reason for choosing small vector fields. So I choose my epsilon to be small enough. I mean, in this case, it doesn't matter because the global vector fields are defined on all of R3 and everything makes sense. But we'll still make this choice. So choose the usual vector field d by dx2 in the y direction, but scale it by epsilon. And I want to parallel transport these vectors which are pointing along the y direction along the x-axis up to length epsilon. So I basically want to go from 0, 0, 0 to epsilon 0, 0. So if I parallel transport that, what should happen? And you have already seen what should happen. So if we start with the standard vector 0, epsilon 0 at 0, 0, 0, which is what epsilon del 2 is, and I start transporting it parallelly along the x-axis, it cannot simply stay that way. It has to start rotating in the YZ plane, right? Because that's what the spiral staircase says. And that's precisely what you should get if you solve the parallel transport equation, that y tilde t, which is the parallel transport of epsilon delta 2, simply starts rotating along the YZ plane. and there's no contribution to the x. So there's still a vector which is perpendicular to the x-axis, which means there's no contribution to the first component, but it starts rotating in the yz plane, which is exactly the same thing that we saw in the spiral staircase, except that you're going up z-axis, now you're going up the x-axis. All right. So I'll just pause here for a minute. Just make sure that you understand why you expect this to be the case, and then later on you can go back and check that this is indeed the parallel transport. Is that clear? Okay. So you expect this kind of rotational phenomenon. Okay. So it satisfies this thing that so your that y tilde of 0 is 0 epsilon 0, which is what epsilon delta 2 is at the point 0, 0, 0. And then you're parallel transporting this along the x-axis, but the x-axis could be thought of as just the integral curve of the vector field epsilon del 1. So that at time 1, you land up at epsilon. Okay? Okay. So this is something you can simply write down and check, because the epsilon is a constant. You can pull that out and then you can check that this is true. So you want to do something similar. So the reason why I'm doing it this way is that what you really want is you want to ask a very naive but natural question. If I have two vector fields x and y, if I parallel transport x along y, and if I parallel transport y along x, does it give me the same answer? That's a very natural question to ask. In the case of Lie brackets, we could ask flow along x, flow along y, or flow along y, flow along x. And usually they do not add up to the same thing, which means they do not commute, which results in the Lie bracket. Okay, and so the Lie bracket is not the only difference, but the Lie bracket is the first correction term in the difference between flowing by x and flowing by y, or flowing by y and flowing by x. So this is it's the similar kind of question. You want to take two vector fields, parallel transport one along the other, parallel transport the other along the first one, and then you basically get like four sides, and then you're asking whether the four sides close up to be a square, like in the case of flows of two vector fields and the Lie bracket. Okay. So if people have seen this picture of Lie bracket, then it should resonate. If you haven't, then you can probably go back and have a look at one of these books where they talk about this. So that's what we're trying to do. Compare how the parallel transport of one with respect to the other, agree. So yeah, in a similar manner, we can parallel transport epsilon delta 1 along the y-axis up to a length epsilon. So again, what happens? You are parallel transporting a vector in the x direction along the y-axis, but that means the vector epsilon 0, 0 as it moves up along the y-axis should start turning in the xz plane, which means it should have a phenomenon like this, and then you check whether it's cosine and sine and whether there are sines anywhere, but this is the corresponding solution. So it starts rotating in the xz plane. Okay, so it's clear that these y tildes and the x tildes are the tangent vectors at the respective points. Namely, x tilde, for example, is the tangent vector at 0 epsilon t 0. Y tilde is a tangent vector along the y-axis at epsilon t 0, 0. Along the x-axis at epsilon t 0, 0, because you're parallel transporting, obtaining y tilde as parallel transporting epsilon 0, 0, 0 epsilon 0 along the x-axis. Okay. So it starts at t equal to 0, which is 0, 0, 0, and then you just move along the x-axis. Same with x tilde. Okay. So yeah, so we simply evaluate both at t equal to 1 and see what we get. Okay. So you take x tilde at 1, take y tilde at 1. So these are tangent vectors at, see what is y tilde at 1? Y tilde at 1 is this expression plugged in t equal to 1. But it's a tangent vector at epsilon 0, 0. If you consider the tip of y tilde at 1, this is simply going to be the vector, the base point vector epsilon 0, 0 plus y tilde at 1. That is what we mean by consider the tip. So that's a vector that I want to consider. And I want to consider the corresponding vector for the tip of x tilde 1, which means 0 epsilon 0, which is the base point, plus x tilde at 1, which means plugging in 1 here. I want to take these two tips and ask whether they are the same. If they are the same, then that would mean that the parallel transports commute, right? So that's what I'm calling tau. So tau is going to be, you take the tip of y tilde 1, which means plug in t equal to 1 here, you get the base point epsilon 0, 0, plus the vector at the base point, which is epsilon, and you plug in t equal to 1 here, you get epsilon cosine epsilon minus epsilon sine epsilon. I've pulled an epsilon out because I can pull an epsilon out from this whole equation. I can pull an epsilon out from the x tilde as well. So this is the tip of y tilde 1. I subtract from that the tip of x tilde 1, which is the base point of x tilde 1, which is 0 epsilon 0, and then x tilde 1 itself, which is epsilon cosine epsilon 0 epsilon sine epsilon. All right. Okay. So I just leave it here for a moment or two. And if you have any questions regarding what we have done so far, you can ask them. We'll see some pictures in a moment. Okay. Are there any questions? Okay. So this is the picture. Okay. So of course, I couldn't really draw a 3D picture. Ideally, this is a 3D picture. So this is the x-axis at time epsilon. This is just length epsilon. This is the y-axis. And if you parallel transport the blue vector along the red vector, you'll be obtaining something which is basically pointing upwards towards you, because it has started rotating along the xz plane, because you're sort of taking the blue vector and parallel transporting along y. So the blue vector will trace out a spiral with the axis being y. So this blue vector here ideally is something which is pointing towards you if you're looking at the screen now. Okay, but it still has length epsilon because of metric compatibility. Same thing with the red one. So the red one, it sort of is pointing inward, but it still has length 1. Okay, so this is not a 3D picture because I couldn't really draw a nice 3D picture which would convey the idea, but hopefully the idea is clear that this blue is basically whatever you get by starting to rotate this blue vector as a spiral as I move up, and this blue is going to point slightly towards you, and the same thing with the red, depending on how the spiral is going, clockwise or anti-clockwise. So the red also has length 1, but it is not on the XY plane, it is away from the XY plane. Okay, but the point is that these two are not the same. And that's what tau is measuring, right? So tau is, you can see here that tau is clearly non-zero. Okay, I mean, you just compare, say, the first coordinate, for example, you'll say that the first coordinate is non-zero, or the second coordinate. Okay, so this is what tau is, right? So tau is, you look at the tip of y tilde at time 1, so this should be 1, but forget that, this is, I put epsilon here. So this is this, yeah, so if you put epsilon, so it's basically this, the base vector plus the tip. So this is this vector, and then the base vector for x tilde plus the tip. So the difference is precisely this vector tau, which is non-zero. Okay. Now I've added 2 more vectors. One is tau 1 and one is tau 2. And this is something I can simply add by hand. So because x tilde epsilon is not on the plane, but it is of length epsilon, x tilde epsilon cannot be the vector epsilon epsilon 0. It is simply pointing slightly upwards. So there is a non-zero vector tau 1, a unique vector which closes up this triangle. Simply define tau 1 to be the difference of epsilon epsilon 0 and x tilde epsilon. Same with tau 2. So I can complete this figure into a square. The square is something which is planar. It lies on the xy plane. The blue vector here, the red vector here, and these black vectors here are of course not on the xy plane. They are actually in R3, but not on the plane. All right. So I mean, this is an important picture. So I'll pause here again for a bit. If do you have any questions that you want me to maybe clarify or go back in the previous slide, just feel free to ask me. Okay. Okay, so you might ask, I have these dots, and I said I'm completing the square, but is there a geometric reason behind completing the square? So you should think of the square really. Remember, we talked about Lie bracket. Think of the square really as saying that if I take the flow associated to the vector field d by dx1, the flow associated to the vector field d by dx2, these two flows commute, because the first flow is simply saying flow in the horizontal direction, the other one is saying flow in the y direction. But those two flows commute, which means if I flow along this vector, the blue vector field for time epsilon, and then flow along the red vector field for time epsilon, in the original vector field, or I flow first by the red and then by blue, they're the same. And that is captured by the fact that the Lie bracket of del by del 1 is with del by del 2 0. Okay? So that the Lie bracket being 0 tells me that if I flow, the flows of the two associated vector fields commute with each other, which is precisely the reason for this dotted arrow being a blue arrow, because this is simply the integral curve for the same vector field down here. So this closes up because the vector fields commute. So this is the usual picture that you get if I take d by dx and d by dy. The flows is if I flow for time 1 in x and then y, or time 1 and time 1 in y and then x, it will always form a square. Okay, so that's the reason. This is not just a whimsical idea to just complete the square. So the failure for flows to commute is detected by the non-zeroness of the Lie bracket. In general, if I am not in a coordinate system where I have d by dx1, d by dx2, if I just have two arbitrary vector fields, usually the Lie bracket is not going to be 0. In which case, I cannot expect this to close up to be a square. I will expect this blue arrow to be something like this red arrow to be something like this, and then it will typically be open. And that discrepancy is captured up to the first non-trivial error term in the discrepancy is the Lie bracket. Okay? So in general, we expect something like a pentagon, not a square, if you are not in a coordinate system where the Lie bracket is 0, right? That's the first remark. The second remark is, if you say tau 1 is 0, suppose tau 1 is 0, it is not 0 in this case, but what would it mean to say tau 1 is 0? Tau 1 is 0 would mean that I have taken the blue vector field, parallel transported along the red, and I've obtained this x tilde epsilon. But I already have the blue vector field defined at this point, which is this original blue vector field. So saying that tau 1 is 0 simply means that in this particular case, simply means that I can take the blue vector field, parallel transport along the red. What I obtain is the original vector field that is already defined. I don't get anything new. So which means the flow and the parallel transport actually agree, right? So, okay. I mean, if you parallel transport this blue vector field along the red, what you get is this parallel transport, but that happens to agree with the vector field already defined at that point. That's what I mean. Same with tau 2. But this is going to be a rare instance. Usually tau 1 and tau 2, as you'll see, is not going to be 0. So, and there are other issues of whether we actually have a square. So what happens when tau is 0? Well, that is precisely what we are trying to capture. So I think right now we're at the heart of the whole concept of torsion. So tau equal to 0 is really what we're after. And this tau, as you'll see in a moment, is secretly what the torsion is. Okay. So I'm going to say this informally, and then hopefully I'll make it a little more precise. So the torsion should be really thought of as the first order discrepancy of the difference between the flows, the parallel transports commuting. So if you take the blue parallel transport along the red, you get this vector. If you take the red parallel transport along the blue, you get this vector. And then these two do not agree, and the discrepancy is captured by some vector. But if we expand that in suitable powers of epsilon, for example, the first term in that expansion is going to be this quantity. I mean, the discrepancy is tau, of course, but when you expand tau and look at the first term that shows up, that term is going to be the torsion. Okay, so the torsion really, in some sense, measures, in this sense, measures the non-commutativity of parallel transporting a pair of vector fields one along the other. Okay, so this is informal, but I'll say it more precisely in a minute. Okay. So yeah, so this is what we're after. So if tau 1 is 0, is tau 2, then of course tau is 0. But in general, what happens? Because tau 1 is equal to 0 is equal to tau 2, as we said, is just too stringent. Usually that will never happen. Okay. And we'll see a picture with the pentagon. So it could be that tau 1 is 0, tau 2 is 0, but the square is not a square, it's a pentagon, that the Lie brackets don't commute. So you could still have things like that, right? So anyway, are there any comments on this picture? So I want to make some like remarks regarding the expansion, and then I'm going to go to the main picture. Okay, so now let's expand. So remember we had this, let me go back one slide, allow me to do that. So we had this tau, correct? And we obtained this by simply saying, look at the tip of y tilde, look at the tip of x tilde at t, plug in t equal to 1. Take the difference, okay? But in general, you can expand this in powers of epsilon and see what you get. And that's what we're going to do. Let me do that. So if you expand in powers of epsilon, you will simply get epsilon square into 0, 0, minus 2 plus order of epsilon cube. Why is that? Because you see, you have a term of the form epsilon cosine epsilon. What is cosine epsilon? It's 1 minus epsilon squared by 2 plus epsilon to the 4 by 4. You have this whole expansion for epsilon small enough. If we expand that, same with sine, you'll see that there are no constant or linear terms. You have epsilon square, and then the other ones are cubic and higher. So that's just an illustration of expanding cosine and sine, nothing more, okay? However, you note that what is this quantity? Epsilon square 0, 0, minus 2 is fine, but if you calculate the torsion of epsilon del by del x2 with epsilon del by del x1, this torsion is nothing but, you can pull out the epsilons because this is a tensor, so you get an epsilon square. This is the torsion of del 2 with del 1, but that we calculated, torsion of del 2 with del 1 was minus 2z. Correct? Because we calculate the torsion of xy to be z, so the torsion of yx, because you're switching, is minus 2z, and that's precisely what this quantity is, right? So that's what I meant by this essentially being the torsion. So if we expand tau, the first contribution is the torsion of the two vector fields under consideration, the vector field epsilon delta 2 and the vector field epsilon delta 1, but it has higher correction terms, and those are higher order terms. So if you were to zoom in with a microscope and ignore all epsilon 3 terms, for example, then what you get is precisely the torsion. So you should really think of this picture as a formal picture, but when you read it, you have to read it modulo higher order terms. And then this picture is going to recover the torsion for you. Okay? So are there any questions, conceptual or computational, up to this point? So this is a nice picture because the Lie brackets are 0, so it's a square, but then you have this extra sort of triangle. We'll see what tau 1 is and what tau 2 is. Okay, you can in fact imagine what it's going to be. And for those of you who do remember how parallel transport gave rise to connections, remember how did we discover, how did we define our connection? Well, we said if you want, you sort of look at a vector and then you parallel transport, what you get is this, but then you already had a vector at this point, which is this blue vector, and these two vectors are tangent vectors at the point 0 epsilon 0, this blue vector and the dotted blue vector. You take the difference and then take a limit dividing by epsilon and so on. What you get is going to be the covariant derivative of one vector field with respect to the other. That is how the connection was defined, right? So this tau 1 is not a limit, but this is an actual thing, which means if we expand tau 1 like we did for tau, the first term that shows up is going to be the connection. And then you're going to have higher order terms, because the connection, remember, is nothing but the first term that you get when you take the difference of the parallel transported vector minus the actual vector at that point, and then you divide by delta t and you take a limit. So this tau 1 is going to be closely related to covariant derivative of x with respect to y, and tau 2 is going to be related to covariant derivative of y with respect to x. And this tau has a lot of stuff, but the main term there is the torsion. So this is kind of a nice triangle which relates to the first definition of torsion that we had seen, that the torsion is by definition nabla xy minus nabla yx minus the Lie bracket xy, right? That was the definition. So you might say, okay, ideally I should get four things. Tau is one vector, tau 1 is another vector, tau 2 is another vector. What about the fourth vector? Well, the fourth vector is the Lie bracket, but the Lie bracket is 0 in this case. And so there's nothing that contributes to a vector here, which ideally should have opened up and gave you a pentagon. But now it gives you a point, and hence you actually have a square, and now this degenerates to a triangle. So that's the setup we're heading towards in the general case. Okay? But this is the precise picture that you get from Cartan's example. Okay? So if there are no questions, allow me to move on. Okay? So I'll let you compute this. If you have followed this other expansion, you can compute this as well. You can show that, as I said, if you expand tau 1, then if you ignore order 3 terms, this is simply the covariant derivative of epsilon del 1 with respect to epsilon del 2, and same with tau 2. So it does look like the original definition of connection. Okay. All right. So a remark is that you can always choose vector fields x and y to be coordinate vector fields to do local calculations, in which case the Lie bracket always vanishes. And you can always rescale these vector fields to ensure that whenever you're flowing for small times, these flows are inside an open chart. And the exponential map also maps things inside the open chart, so that you can do add and subtraction of all these things by essentially doing it in a small open chart. But for that, you might have to rescale your vector fields to be of sufficiently small length. Okay. So, but it can be done. Okay. So, yeah. So as we saw here, basically, if you do it locally in a patch, tau 1, tau 2, and tau essentially can be replaced by nabla yx, nabla xy, and the torsion up to higher terms. Okay. Okay. So that's the first sort of main step towards what torsion is. So it's sort of secretly saying that you want to measure the failure of whether parallel transporting one against the other and then the other against the first one, whether they agree. Okay. So let's return to the general case. We have a torsion. This is an arbitrary connection, and these need not be metric compatible. And the vector fields x and y are generally local vector fields, which may not have the property that the Lie bracket is 0. However, all the pictures that I'm going to draw, there's at least one big picture, is in some chart, so that I can add and subtract vectors as I wish. I cannot really add and subtract tangent vectors at different points in the manifold, but I can do it if I have a local chart where I can trivialize everything and use parallel transport. So that's what I'm going to do, but the setting is x and y are local vector fields, but the Lie bracket may not be 0, and the connection need not be metric compatible. Okay. I'm going to use a notation. So if I parallel transport x along y, I am calling that x parallel. Similarly, if I parallel transport y along x, I'm going to call that y parallel, because there's only one other vector field which I can parallel transport along. Okay. Okay, so this is the picture that you get. And let us look through this picture carefully. So you have x here and you have y. These two need not be perpendicular. They're just vector fields. And I'm parallel transporting this x along y, along the integral curve of y, for example. What I get at the end is going to be this. So this x per parallel is going to be this vector parallel transported along this curve, along this integral curve generated by y itself. Okay, so that's the picture. What is this blue vector? This blue is the vector field x at this point anyway. You see, x is a local vector field defined on this whole patch. So at this point, x is defined. So that's what this is. This vector is the parallel transport of this blue line along this curve. Okay. So we have two things, x and x parallel. What about y? Well, you can parallel transport y along x. What you get is y parallel, which is this red vector. And y, of course, makes sense at this point itself. So this is the vector field y at this point. Now, why should we expect this triangle? Well, this is something we just discussed. How do you get a connection from a parallel transport? Well, you take this vector minus y, divide out by, by the length of this thing, and then you take a limit. So this is going to be the linear term, so to speak, that appears when you expand y parallel in terms of y and other things. Same with this triangle, right? That this is going to be not the only term, but this is, you have to read it modulo higher order term. So x parallel minus x is going to be the length of y times this plus higher order terms. Okay. Now what about this? Well, this is going to turn out to be up to higher order terms, the torsion of these two vector fields. And this thing, which we're calling the pentagon, and so on, this is going to be the Lie bracket. This is again up to higher order terms, simply because if I flow along x and then flow along y, or I flow along y and then flow along x, clearly it does not go to the same point. So the discrepancy is non-zero, and the first non-zero term in this discrepancy is the Lie bracket. So this is a picture valid, but modulo higher order term. So you really have a pentagon. This captures the failure of the flows of x and y. You have another pentagon. This captures the failure of the parallel transports, whether they commute when you switch vector fields. And these two appear because this is just saying that you can derive the connection from the parallel transport. And these four fit into a quadrilateral. But if you ignore higher order correction terms, then this quadrilateral is precisely the first definition of torsion. This is saying that this quantity is nothing but, I think I might have switched. Yeah, so it's this, the arrow is correct. So this is nabla xy minus Lie bracket xy minus nabla y. So it matches up with the very first definition. Okay. So is this picture clear? If you have any, so this is sort of the main picture that I want you to take home. I mean, even though all the formal details may not be immediately clear to you, but this is really the picture that you should try to understand if you want to understand what torsion is. Okay, I mean, this is, in my mind, the most geometric sort of interpretation of torsion. So that it connects all the relevant geometric quantities in a very nice picture. In the Cartan spiral staircase, this became zero, so it degenerated to a square, and then this quadrilateral degenerated to a triangle. But it had more or less all the key ideas in there. Okay. So any questions on this? Okay. I mean, it will take some time to go back and maybe read through this thing, work out the Cartan example, because that's a very concrete thing, and see what this thing is. So this, of course, makes sense again if you choose x and y to be small enough so that all the things make sense in a local chart and everything is happening in a chart. So you have a bit of writing down to do to make sense of this, but hopefully the Cartan spiral staircase example illustrated why we expect a picture like this. Okay. So yeah, it should be understood modulo higher order terms, which we know already, but it's clear why the shapes are the way they are. So this is the defect of the flows commuting. This is the defect of the parallel transports commuting. This triangle is how you derive connection from parallel transport and vice versa. This is the same. So that explains the figure. Okay. So I think we're more or less done. So let me just end with one slide. So yeah, so this is something we have been talking about. You can define torsion as the failure of parallel transports to commute, but you really have to go to the more geometric definition of connection, namely that coming from parallel transports, to talk about the geometric origin of torsion. Okay, you cannot simply define it by the connection and expect it to be naturally geometric. So yeah, so the point is, as Cartan's staircase suggests, if you have a metric compatible connection, and if you take a frame, remember we chose the z-axis, and then we said if I take a stick pointing in the y direction and I move along the z-axis, the sticks basically start rotating, staying perpendicular to the z-axis. So that's basically talking about twisting, right? So if I choose the x-axis, a vector pointing in the y direction and a vector pointing in the x direction, and I parallel transport that along the z-axis, both of them are going to start rotating. So this twisting is what was the reason behind calling this a torsion, because it's sort of as if it's twisting and bending around a certain axis, and in this case it's twisting and bending around a geodesic. Okay, so hence the nomenclature called torsion. So I think if you want to read more about how these things appeared originally in Cartan's work, and then what was his motivations behind defining torsion arising from physics, geometry, and how it's used in modern field theory, I think this is a nice article. At least parts of it is quite readable to read, especially if you have some basic training in physics. You might be able to appreciate it more. So this is available online. It's also available on, I think, one of the author's web pages. So it's called Elie Cartan's Torsion in Geometry and in Field Theory, an essay. So this picture that I've drawn here is also something that is present in their paper. Okay. So, okay. So are there any questions regarding the whole thing? Any questions on the first few slides or in the middle? All right, so maybe let's stop here for today then.